Welcome back. Section 13 continued. So we are to here. Last thing in the previous recording was this example that you can kind of see right at the top of the page. So now is where I explain that there are three principal methods by which heat can flow, called conduction, convection, and radiation. Conduction, as it says here, heat transfer by collision of particles, either molecules or electrons or some of each. This is what happens if you put a cold frying pan on a hot stove, for example. Remember, the temperature is telling you the average kinetic energy per molecule. So the hot stove, the molecules are shaking around more vigorously like that. On the bottom of the frying pan at a lower temperature, they're shaking around less vigorously like that. You put the two in contact with each other, and the more vigorously vibrating high temperature molecules start colliding with the colder ones on the bottom of the frying pan. The tendency, averaged over many, many collisions, and there will be a lot of them because there's a lot of molecules involved here. The tendency is for things to even out. The faster moving molecules tend to get slowed down. The slower moving molecules tend to get sped up. And in this way, energy is transferred from the stove to the bottom of the frying pan. And then it continues, the energy continues to flow through the frying pan by the same process that the faster moving molecules on the bottom of the frying pan are colliding with its neighbors in the next layer up. And again, things tend to even out. Aside from molecular collisions, frying pans tend to be made out of metal. A good deal. Metal's full of free electrons. That's why they're good conductors of electricity. Those same free electrons that can be made into an electric current, if you hook the piece of metal to a battery, those same free electrons are also very effective at carrying thermal energy. That you've got these electrons that can just whiz around and go all over the place inside that frying pan, and they will carry energy around and even out where it's located as well. So the molecular collisions and also the motion of the electrons, that they get bumped into and sped up, and they carry the energy. And that's how heat flow by conduction works. That's why it's a bad idea to stick your tongue on a metal fence post in the middle of winter, because metal is a really good conductor of heat for the same reason that it's a good conductor of electricity. And it'll just suck the heat right out of your tongue and freeze all that spit and turn it into basically an adhesive. Whereas if you stick your tongue on a wooden fence post in the middle of winter, it doesn't go nearly so badly for you. I would still question why you wanted to do it, but so that's conduction, and details will follow in a matter of seconds here. But just to round out the introductory list, convection is heat flow by a transfer of heated material. For example, if you have a fireplace and you've had a fire in there, but when the fire's done, you forget to, it's the middle of winter time, it's 10 degrees Fahrenheit outside, you forget to close the damper. Well, all night long, hot air continues going up the chimney because the 70-degree air inside your house is less dense and therefore more buoyant than the cold air outside the house. So you get heat flowing up the chimney, and it makes your heating bill higher than it needs to be, and that's an example of convection. Radiation is heat flow by electromagnetic radiation. This, for example, is how heat gets from the sun to the earth. The earth doesn't touch the sun, so there's no heat flow by conduction, and there isn't really a significant amount of transfer of material from there to here. I mean, there's the solar wind, but it's really, really thin. It doesn't play a significant role in heating the earth. So there's no convection, but we are constantly bathed in electromagnetic radiation in and around the visible part of the spectrum mostly. And that's how the heat gets from the sun to here and keeps our planet a lot warmer than it would be out in interstellar space. So conduction, convection, and radiation, those are the ways the heat flows. Let's describe conduction, first of all. Conduction. So here's a little chunk of some material. Could be a pane of glass in a window in somebody's house. And the outside of the house is some temperature T1. Maybe it's 40 degrees Fahrenheit outside. T2 is the temperature of the other side of this pane of glass. Maybe it's 70 degrees Fahrenheit inside the house. Now, as usual, I'm oversimplifying a little bit. There would be a layer of cold air against this side of the window and a little layer of, I'm not very thick, but a little layer of warm air against this side of the window. And we're just saying if it's 40 degrees outside, it's 40 degrees right at this surface of glass. And if it's 70 degrees inside, we're saying it's 70 degrees right on this surface of the glass. A for area. This is the amount of area that the heat flows through due to the difference in temperature. Heat from inside the house wants to flow outside the house, okay? Heat soaks through the window by the process of, well, glass is not a good conductor of electricity. It would be pretty much just the molecular collisions in the case of glass, okay? But heat soaks through the window by the collision process between molecules that I was describing earlier. Actually, to be completely general, let's say you've got a really thin window. I'm going to start out with infinitesimals like I quite often do with these types of discussions, because that way you're covered no matter what's going on. If it's your house in the outside, you've got a pretty stable situation. It's going to be the same minute after minute after minute. But if you want to be able to apply this in a case where the temperatures might be rapidly fluctuating, and also maybe one part of the window is at a different temperature than a different part of the window, you have to break everything down into little pieces. So the rate of heat flow through this thing remember, time, a rate is a time derivative, okay? Or at least if you're talking about the rate with respect to time. And I better label things carefully because I'm going to have little t for time and capital T for temperature in the same equation. So this one is time. So do you have heat flowing through the window rapidly or slowly? What does that depend on? Well, maybe I should just write it down and then explain what each part of it is. Capital T for temperature over here, little t for time. One of the things the rate of heat flow depends on is the temperature gradient. It's to some extent stuff that flows is stuff that flows. Whether you're talking about water flowing down a hill, or whether you're talking about heat flowing through a window, or whether you're talking about an electric current flowing through a light bulb, a lot of the principles are the same, really. And just as water will flow faster down a steep hill than it does down one that's not very steep, heat will flow faster down a steep temperature gradient, okay? So a bigger difference in temperature, all else being equal, that'll make the heat flow faster. A thicker window makes the gradient not so steep. A thicker window will, that's an inverse thing here. That'll make it flow, the heat will flow not so fast if it's a thicker window. The area A, you lose more heat out of a big window than out of a small window. Probably there's no surprise there. I probably don't need to elaborate too much on that. K is a property of the material called its thermal conductivity. It's going to be higher for a piece of steel than it is for a piece of wood. This is the reason why you don't want to stick your tongue on the piece of steel in the middle of the wintertime. My stepdaughter did that once, but don't tell her I told you so. Came in, she was just a little kid. Came, probably her friends dared her to do it. They'd seen that Christmas movie or something. Tongue was bleeding. It was, anyhow, like I said, I never said that. You don't know. Shh. Thermal conductivity of the material. K, and this one is not tabulated in your reference handout because it's one of these things where, you know, we're going to need that number for one homework problem in the whole course. Is it really worth the space in the handout? I'll just include the number in the question. But K would be a large number for a material like copper. K would be a very small number for a material like asbestos. Asbestos is really wonderful stuff. It's got a lot of great properties aside from the fact that it'll kill you. It's just great. So let's just modify that a little bit. The example that's coming up is the wall in somebody's house where you've got several different materials sandwiched together. You've got a layer of sheetrock or plasterboard or whatever you want to call it. And then beyond that, there's the insulation inside the wall. And then on the outside of the house, you've got a layer of wood. And so if you've got several materials that are in contact with each other, and I'm going to assume a constant flow rate. So everything is nice and uniform with respect to both space and time, and that eliminates the need for the infinitesimals. I can have, just some finite number for the thickness of the window instead of having to. What's going on here is if you had a piece of glass that was 1/4 of an inch thick, you'd have to integrate, okay? You'd have to break it up into lots of little infinitesimal thicknesses and add and if we assume a steady state, there's no need for that sort of thing. So a little sketch of what's going on. So you got a layer with one conductivity up against a layer with a different conductivity and so on. And I don't want to, I got a bunch of little dots here because I don't want to look like I'm being specific for any exact number of substances. This could be 2 different materials. This could be 29 of them. But the inside surface here is T2 and the outside surface there is T1. And so now and I'm not going to bother writing out the details that get you from here to here, but the idea is this would apply to each one of these materials, and you put it all together, and plus make a couple of substitutions. But now it's delta Q over delta T because I don't need infinitesimals anymore. The minus sign, by the way, same minus sign we had back over here. That's because heat is being lost by your house. Okay, heat is flowing outward. Once again, we have the area A. For this, where this little infinitesimal difference in temperature was, well, now I've got a finite difference, T2 minus T1. Okay, for the dt. And then the other thing is the thickness of the material, which I meant to label and I didn't leave myself enough room. Fix it real quick. Forgot to put this on there before. L1 for the thickness of material number 1, and L2 for the thickness of material number 2, and so on. So L would go where I had this dx before. And I'm going to kind of package that together with the conductivity by rearranging things like this. You put it all together for these different materials, this denominator would be L over K for material 1 plus L over K for material 2 plus L over K for material 3, and so on for however many of them there are. So this is kind of like, you could consider this one back over here to be the general definition for the thermal conductivity. And then here we've kind of taken that equation and adapted it to this. all over K. The thickness of the material divided by its conductivity is called the R value of the material. Like if you go over here to Home Depot and buy some fiberglass insulation, and it says on the wrapper what the R value for that insulation is, you know, put the insulation in your attic, you know, lower your heating bills. That's what we're talking about here. So you add up the R values, and that's that denominator there, which brings us to the next example. Gee, wouldn't it be nice if somebody could figure out a way to make this automatically focus? So we have here a simplified house. Probably the most unrealistic simplification is that it has no doors or windows. I guess you must get in and out of the house through a tunnel or something like that. But kind of a small house, 20 feet 20 feet wide by 40 feet long, just a one-story building that's 8 feet tall. And the ceiling is constructed in the same way as the walls. So assuming that heat flows out of this house by conduction only, which is completely unrealistic. A lot of the heat that flows out of a house is penetration of cold air from the outside. I think, well, it depends on how tightly you've got the house wrapped up in caulk and insulation and so forth, but the air in your house probably changes every few hours. You don't want a house too tight or you start getting moisture problems. Mildew and things like that. But I can remember a long time ago reading about some study that somebody was doing of how much does it save on the heating bill with, if they had two similar houses, but in one of them they put a lot more insulation in it, and when winter came they wanted to see how the heating bill was affected by the extra insulation. Well, they couldn't figure out why the house with all the super insulation in it actually had a slightly higher heating bill than the other one. But on a little bit of investigation, they figured out the reason was because the people who lived in that house had a cat or a dog or something, and they were always opening the door to let the animal go outside. And the people in the other house didn't have any pets, and they only opened the door a couple times a day. So anyhow, a lot of the heat loss from a realistic house is from an exchange of air, heat flow by convection, essentially. But if we've got this house just sealed right up tight so that anybody in it's going to suffocate, then how many BTUs per hour would it take to heat it? That is the question. Well, BTUs per hour, heat is measured in BT. Yes, in our world, heat is measured in joules, but in the world of construction, even our textbook had to put these things in British units because nobody uses SI units in the construction industry. It's all feet and pounds and degrees Fahrenheit. And so that's what's going to be in this one here. So BTUs for Q, the heat, hours for the time, BTUs per hour. It's this quantity here. It's asking us to calculate this, okay? And if you go buy a furnace, BTUs per hour is how they're rated. Well, one thing I'm going to need which just barely still shows on the edge of the picture there. I'm going to need the area that the heat flows through. This would be the surface area of all the walls and the ceiling. So here's a little sketch of the house. I guess I'm assuming that no heat escapes through the bottom of it, which is not quite true either, but it's 8 feet tall, 20 feet that way, 40 feet that way. So we've got, first of all, let's start with the top. 40 feet by 20 feet for the top of it. So we've got 800 square feet up there. The right and left ends. Each of them is 8 by 20 or 20 by 8. And there's 2 of them, the right end and the left end. So that's 320 square feet there. And then finally, there's the front and the back. The front and the back are each 40 feet by 8 feet. $640. So if I'm assuming that not much heat escapes through the bottom of the house, which is not entirely true, but it's probably the dirt under the house is probably not as cold as the air outside, at least on a cold winter's day. Yeah, 0 degrees Fahrenheit outside. The soil under the house is probably 40 or 50 degrees. So at least there's significantly less going out the bottom. So this is the total area that the heat is flowing through, 1,760. That's what goes into the formula for A, the area. Now, as for the R values, this is something I did not put in the formula sheet because it would be one of those things where you need it for one homework problem in the entire course. So I'd have to provide this in a question if I asked about it. But if you're not in the middle of a test, the textbook is available to you. And there is a table in the textbook where you can look these things up. And that's where I got these numbers. Half-inch drywall. Actually, for walls, you usually use 3/8. Half-inch would be for ceilings, but this house, it's all 1/2 inch. R equals 0.45. The units on that, are you ready? It's not pretty. Square feet times degrees Fahrenheit times hours over BTUs. So that's the first layer. The heat goes through as it works its way outward. The next layer is where you get most of the resistance, R for resistance. That's the insulation. Half-inch of drywall, 3.5 inches of fiberglass. $10.9 in the same units, or at least when it's nice, fresh, new fiberglass. That's what it's supposed to be after the house has stood there for a while and the mice have been tunneling around in it and doing stuff to it. It's probably not quite so good anymore, but then we have 1 inch of wood on the outside. According to the textbook, that's good for another 0.91. So the numbers are all set up and ready to drop into the formula. Formula once again was the area times the difference in temperature between the inside and the outside over the summation of the R values. So we had 1760 for the area. Temperature inside the house, 70 degrees Fahrenheit. The temperature outside on this particular day is 0 degrees Fahrenheit. The R values. And the numbers just happen to come out almost exactly 10,000 BTUs per hour. So if heat is leaving the house at a rate of 10,000 BTUs per hour, your furnace needs to be putting out 10,000 BTUs per hour to make up for that and maintain the 70 degrees in there. I don't know if you can even buy a furnace that puts out only 10,000 BTUs per hour. That's fairly small, but like I said earlier, realistically, your house is going to lose more than this because it's not just conduction that takes heat out of the house. Okay, that brings us to where it says convection. Oh, where can I get that where it doesn't tip? Well, how much do you really care if it's not perfectly level writing anyhow? So that was a little bit about conduction. Convection, I'm not going to get into in much detail. I'm just going to mention it to fill out the list. I've already said convection is heat flow due to the flow of heated material, like for example, the heat flowing up a chimney. If any of you are going into meteorology, I've occasionally had students in this. Last I knew, they had a meteorology program at Brockport, and I've occasionally had students go through this course who wanted to go there and do that. Convection is a big deal in the weather. That's one of the main processes that makes the atmosphere circulate around and brings us our weather. But moving on, radiation, such as the sun heating the earth with electromagnetic radiation. Heat flow by radiation is described by Stefan's law, which I will write down for you. Sometimes called, it depends on whose textbook you're reading. Sometimes it's called the Stefan-Boltzmann law instead of just Stefan's law. As I understand the story, Joseph Stefan found it from experimental data in 1879. Ludwig Boltzmann showed how to derive it from theory 5 years later. So sometimes they both get credit. Sometimes it's just the guy that discovered it but couldn't explain it. Power radiated by a light bulb or the sun or a glowing piece of metal that a blacksmith has just pulled out of a fire, whatever it is that's giving off electromagnetic radiation. Maybe I should point out, in spite of the different notation, this is telling you the same thing as this, okay? Power means energy delivered per unit time. So here it was delta Q over delta T measured in BTUs per hour. Here it's P for power measured in joules per second, watts in other words. Well, BTUs per hour, joules per second, it's energy over time in both cases. This is telling you the rate that energy is flowing due to this particular type of heat transfer. We have a proportionality constant, often called the Stefan-Boltzmann constant. The Greek letter sigma is going to stand for that, a lowercase sigma. Capital sigma is the summation symbol that we use all the time. So let's see, I need some places to label things here. The Stefan-Boltzmann constant, if you're working in SI units, which unlike the construction industry is what's usually used here, 5.67 times 10 to the negative 8, that would be measured in watts per square meter times Kelvin to the 4th power. K is for Kelvin, degrees Kelvin. A is the area doing the radiating. In that respect, it's the same as heat flow by conduction, where if you've got twice as much area, twice as much heat can flow through it. temperature. For all these relationships, whether it's PV equals nRT or Stefan's law or any of a bunch of other things that we'll encounter as we look at thermal physics at one point or another, you need to count all the thermal energy that's there, not just the part that's above the freezing point of water. So if somebody slips you degrees Celsius, it needs to be converted to kelvins. It's the absolute temperature. It isn't that often that you encounter something to the fourth power. A lot of stuff in physics is linear, not that unusual to have something squared, kinetic energy, 1/2 mv squared, or the force of gravity is proportional to 1/r squared, but t to the fourth power, that's steep. If you just double the temperature, let's see, 2, 4, 8, 16. 16 times the rate of heat flow if you just double the temperature. 3 times the temperature, I'm not going to try and figure that out without a calc. Well, let's see. That'd be 81. 3 times the temperature, 81 times the power, and so on. And then E here is a property of the surface called its emissivity. I'm just going to put that over here. Is that on screen? Not really. Let's kind of slide this over a little bit. EMISSIVI. Emissivity is a property of the surface of the glowing object. The extreme values, I can't be any smaller than 0. It can't be any bigger than 1. It depends on the surface. E equals 0. That would be a perfect reflector. A mirror has a very low emissivity. Or, if you had like a ball of metal and polished it all up real nice so it had a mirror-like surface. Well, you wouldn't have made it to a perfect 0 for the emissivity, but it would be a fairly small number. A surface like that light has a hard time getting through from the outside. That's why you see your reflection so nicely in it. If light has a tendency to bounce back the way it came when it comes from the outside, light also has a tendency to bounce back the way it came when it approaches the surface from the inside. Okay, so if you had a perfect mirror that reflected 100% of the radiation that hits it, then it doesn't matter how hot you get that thing, and it doesn't matter how big it is, no radiation is getting out. But that would just be an idealized extreme. Real mirrors would have, point something fairly small for their emissivity, but some would escape. The opposite extreme, E equals 1, is called a black body. Black body is called a black body because, the thing that's black about it is it's a perfect absorber. It absorbs 100% of the radiation that hits it. A black body would also be a perfect radiator. The way you would make a black body, you get some great big tin can, like a 55-gallon drum, okay? And you drill a little, like you get a 1/4-inch bit on a drill, you just drill a little hole in the side of it. So you've got this great big cavity with this tiny little opening in it. If you have a laser pointer and shine it on that, well, how much light gets reflected off of a hole? Perfect absorber, okay? All the light goes in. Well, once it's in there, even if the walls are not particularly absorbent, that light's going to reflect around many times, and the odds of it finding its way back to the hole again are pretty much zero. It's not coming back out. If you take this and you get it hot, so that you establish a radiation field inside of there, okay? This tiny little hole does not really significantly affect that radiation field being in equilibrium with the walls that absorb the light over and over. Absorb, re-emit, absorb, re-emit, absorb, re-emit. The walls are in equilibrium with the radiation they contain, and a little bit of light leaks out through the hole, and that's your perfect radiator. A black body is a big deal, actually, when you get into the history of physics. The spectrum of the light coming out of a black body failed to obey the predictions of classical 19th century physics. And that was one of the experiments that led into the development of quantum mechanics. And if you take the third course, Physics 133, you will look at black bodies in, let's just say they come up again, very definitely. But anyhow, what we're talking about today is Stefan's law, the rate that energy flows due to radiation. And I have an example to run through, and then I think, isn't that the end of this section? Yeah. Next page would be section 14. A couple of weeks ago, no, that was just last week, when I was talking about Kepler's third law. I said that Kepler's third law, as modified by Newton, was astronomers' main tool for determining the masses of stars. Stefan's law is their main tool for determining the size of stars. So here's some data for, I believe I made this fairly similar to, I'm on the next page now, am I? No. Yeah, there it is. I don't think I copied it down exactly, but this was fairly similar to Arcturus, which is a star that's in the western part of the sky in late summer. The temperature can be determined from the spectrum. We don't need to get into exactly how they do that, but well, the basic idea is that at this temperature, the spectral lines of hydrogen become the most prominent, whereas at that temperature, the spectral lines of oxygen become the most prominent. And it's not exactly a simple process, but they can tease out the, plus there's just the overall color of the star. All stars are made out of the same stuff. They're all a mixture of hydrogen and helium. roughly, I mean, it varies by a few percent, but it's basically 3/4 hydrogen, 1/4 helium. Different colors of stars correspond to different temperatures. So you can get a rough idea just from the overall color of the star. And then supplemental information is the prominence of the different elements in the spectrum. But that's where the temperature would come from. As for the wattage of the star, making it sound kind of like a light bulb, well, you can tell the intensity of the light falling here on Earth, how many watts per square, well, it'd be a small fraction of a watt per square meter for the brightness that we receive here on Earth. If you know that, and if you know the distance to the star, and maybe I won't get into how we determine that, but if you know how many watts per square meter here on Earth, and you know how many meters from here to the star, you can figure out the total number of watts of energy that's being radiated by the thing. And so we have in Stefan's law back over here, the question tells us the power in watts. The question tells us the temperature in kelvins. Stars are more or less black bodies. The emissivity is actually 0.9 something. It's not quite a perfect black body. But just for an example in an introductory course, I'm just going to set the emissivity equal to 1, and that's only going to be off by like 3, 4, 5%, something in that neighborhood. So, and of course, this is a fundamental constant. That's always the same. So everything else, you can solve for the surface area of the star, which is just a hop and a skip away from knowing its radius. So maybe I'm over. Well, now let's do it here. So just kind of putting this, recopying the same thing. This is what I'm going to fill the numbers into. For sigma, the Stefan-Boltzmann constant, that number right there. Area. Actually, yeah, let's make a mess out of everybody's notes. I was filling in numbers. I know the power. I should have put in the 3.6 times 10 to the 28 watts. I had a professor once, it was a stellar interiors course that I took when I was a senior. It was a bigger blackboard than this one. He was, I don't know what it was he was showing us, but he was going through this long involved calculation, and we're going along copying it all down, and he gets over to about here somewhere, and he starts looking at what he's written, and he's stroking his chin and starts looking it all over, and he comes back over here. That's where he made the mistake, and we're all just sitting there with our notes, just crossing out about a page and a half worth of stuff we've just done. Anyhow, could have been worse. So I meant to fill that in for P. This goes in for sigma. A is the area of the star. I'm going to try and solve for that. The emissivity Star is approximately a black body. As I said, there is, you could have a better value in there that would be slightly less, but if you're not worried about a real super precise answer, you can just stick in a 1. And as for the temperature, 3,700 kelvins, that gets raised to the 4th power. So maybe I don't need to write out all the line by line algebra. It should be fairly obvious to you here. What you raise that to the 4th power, and then you multiply by this, and whatever number that gives you, you divide both sides. And so kind of fast forwarding through some basic algebra, the area of this would be its surface area, because there's other kinds of area like cross-sectional area. But the surface area of the star, 3.39 times 10 to the 21st square meters. Stars are spherical. Surface area of a sphere and if you ever need one of these types of equations, it's on one of the back pages of your formula sheet. Surface area of a sphere, 4 pi r squared. To solve it for the radius, you would divide both sides by 4 pi and then take the square root. So you put this number in there, divide it by 4 pi, take the square root, and 1.64 times 10 to the 10 meters. Then, of course, anytime there's a question like this, there's always somebody that gets caught by the old radius versus diameter trick. People tend to talk about the diameters of things. If it's a plumber and he's talking about a 1/2-inch pipe, that's the diameter of the pipe, not its radius. And it's the same with stars. People talk about the diameter. So the question says, find the diameter. That's the radius. If you put a little box around that and go on to the next question, well, you'll get most of the points, but 3.28 times 10 to the 10 meters, which, if anybody's interested, is about 24 times the diameter of our sun. That's a pretty big star, although they do come significantly bigger once in a while. Okay. End of section 13.